Okay, today we're only going to add in one new family, although just because of its nature, it does add some weird twists to a couple of things, but nothing too major. I think you guys will do fine with this stuff. But the group we're adding in today are called the aromatics. Now, the first thing we should probably look at is how the aromatics fit into this bigger picture. So in the space next to 1 there, off to the right, let's just draw a little chart. If you took organic chemistry as a whole, it kind of splits into 2 branches or types of organic chemistry that we look at, or types of organic molecules. The first one is the aliphatics, and the second one is the aromatics. Now, the easiest way to differentiate the two is to teach you what the aromatics are. The aromatic molecules are ones that contain a molecule called benzene, and that's what we're going to learn about in this lesson, is benzene, because that's what makes them part of this aromatic family. And aliphatic just really means everything else. So all the alkanes, the alkenes, and the alkynes that we've learned about, and most of all the other families pretty well that we're going to learn about, are all part of that aliphatic group. They're not aromatic. The aromatics are very strictly, they contain benzene, and that's the only definition. So I would put that chart in. You could maybe write some notes there, whatever helps you keep those two separate, but that's basically the gist of what you need to know for now. Now, the reason they're called aromatics is traditionally the aromatic molecules were called aromatics because many of them have very distinctive odors, not necessarily all of them, but many of them did, and so that's kind of where the origin of that term came from. All right, now let's look at what benzene itself is. Benzene has a formula of C6H6. Now, that's a very difficult molecule to come up with in terms of structure. And originally, they thought that arrangement was 6 carbons in a ring, like this. But if that was all saturated, like a cycloalkane, this would be C6H12. And so that doesn't work. So it's got too many H's. So originally they thought that maybe the way this was put together was that maybe there was 3 of those bonds were actually double bonds. So now each carbon in the ring is forming 3 bonds already, and so there would only be 1 H coming off of any one of these points. So that gives you your C6H6. Now, the problem with this setup was that experimentally, when they looked at it, remember I talked a little bit about behavior and the functional groups, these families. If you were to look at this molecule, at least how it's drawn right now, you would think that should act like an alkene because it has 3 double bonds. It should act like it has double bonds, and benzene doesn't. So that told them that this probably isn't the most correct representation of what's going on. Although you may still see this representation used on some questions, maybe even on a test. If you take anything in university, you may still see this representation. It's not the most commonly used anymore. What we think is happening now is we still think there's this 6-carbon ring structure, but the electrons that make up, let's say, that double bond, we know is really just a shared pair of valence electrons. And so there's a shared pair for that one and a shared pair there. And that's what we thought originally, that those were into double bonds. But now we don't think that they're in double bonds because they don't behave like double bonds. And what we kind of think is that all of these 6 electrons, instead of being shared between just 2 carbons, are equally shared between all of them. And so we kind of end up with this pseudo double bond somewhere in between a single bond and a double bond, in between all of them. So now the most common representation, at least the most common that I use for sure, is a 6-carbon ring and then we just draw a circle in the center of it. And that represents that those extra electrons are just being shared equally among all of the carbons. So it's not really a true single bond, it's not really a true double bond, and that's why benzene is kind of just its own thing. It behaves differently, it has different properties than either the alkanes or the alkenes. So one thing to keep in mind is this is not cyclohexene. This is its own thing. This is something completely different. So I'm going to do another video on the naming, just because that's kind of a big subject. So in your notes, jump ahead to the next spot. Let's just talk about the physical properties of some of the aromatics, and then some of the common ones that maybe you need to be aware of. So benzene at room temperature is a liquid. You don't necessarily need to know the boiling point. It's in your notes as 80.1, but you don't need to know that for sure. Just know that this is a liquid at room temperature and that it's nonpolar. That's important when we start looking at things like boiling points and like relative boiling points, and when we're looking at solubilities. So this is a nonpolar molecule, so it would like to dissolve nonpolar solvents, not polar ones. Okay. Some of the common aromatics that you should know are, in the 19th and earliest 20th centuries, benzene was used in many common applications. So it was in a lot of things, actually, until they found out that it had some carcinogenic properties. Now, if you don't know that term, carcinogenic just means cancer-causing. And so now it's not really used in very many things at all. It's still in some industrial products, but not any like household consumer-type products where you're putting this on your skin. It is a very important component of gasoline that we'll learn about in the next half of this unit and why that is. But one way to make it less carcinogenic is by adding different molecules onto it. So one example is if you take a benzene ring and add a methyl group on top of it, that becomes methylbenzene, or its common name is toluene. And that becomes a little bit safer aromatic that we can use. It doesn't have the same carcinogenic properties, or at least much more mildly carcinogenic in terms of that kind of stuff. So it's something that we can use a little bit more safely. Now there's a couple that I'll throw in here just for fun. You don't necessarily need to know these molecules, but I'll throw them in here just because they're kind of cool. Okay, the first one is if you were to take a benzene ring, that is not very well drawn, and you added in structures like this. This is beyond anything that you would be required to name, but if you take that and add those structures to a benzene, then that molecule has is basically vanilla. It has an odor and I believe even a taste of vanilla. So this could be something that would be added like as an artificial vanilla scent to an air freshener or something of that kind of nature. If you took a benzene ring like this and attach it to not another benzene ring, but just another ring of carbons with a couple of double bonds in it, this is called naphthalene. And if you've ever been to maybe your grandma's house or something and found mothballs, this is the chemical that you would find in mothballs. If you've never been around mothballs before, they have a very strong, very potent kind of alcohol-y smell designed to repel moths, and that's that molecule. Okay, the last one. If you take the toluene molecule that I mentioned, that methylbenzene, and then we add some nitro groups like this, 3 of them, you end up with trinitro toluene. And the reason this one I think is significant is because it's TNT. So you can see how dramatically just changing a little bit of functional groups here changes the properties of the molecule. We go from mothballs and vanilla to dynamite just by changing what groups are attached to the benzene group. It also suggests why things like bomb-sniffing dogs are able to find bombs and dynamite and explosives, is because an aromatic molecule like this, even though humans probably can't really detect it all that strongly, the dogs have a much keener sense of smell, and so they can pick up on that. So again, those are not molecules you need to memorize or know for sure, but I think they're interesting just to show how dramatically the properties of these molecules can change with just slight changes to what's attached to the molecule. So hopefully that all makes sense. If you have any questions about this, let me know, and we can go into anything a little bit deeper if we need to. And in the next video, I'll show you how to draw and name these molecules, and how the rules are a little bit different. They're very similar to what we did yesterday with the cyclos, but just making sure that we know how to handle that properly. So see you in the next one.